Hi everyone, in this video I'm going to be going over how to do Euler's method, which is a section from 6.1. So Euler's method is an approach that allows us to approximate the particular solution of a differential equation which is defined by both x and y and passes through a point given to us. So first I'm going to do an example of what this means and what this looks like with a really simple example of just a straight line. So let's say we have a line with a slope of 2/3 that goes through the point 3, 6. We want to use this information to determine the missing y coordinates when x is 9 and then when x is 7. This is a great point to pause the video and see what you can do here on your own, because this really does use your prior knowledge, what you know about lines. Now I'm going to show you my way of doing this. There are a couple ways you might have thought about it, but in the end we're going to have the same result. So the first thing I'm thinking is to get from the point 3, 6 to the point where x is 9. I'm thinking about how much my x values are changing from that point to the new point. So my change in x from 3 to 9 is, of course, 6. And so then I'm thinking, if I'm moving to the right 6 units and I have a slope of 2/3. I know a slope of 2/3 basically means that for every unit I move to the right, my y value is going up by 2/3. So if I'm changing 6 times to the right, that means I'm going up 2/3 6 times. So I can just multiply 6 by 2/3 to get my change in y, which would be 4. So that represents like how much my y values are increasing from when x is 3 to when x is 9. And then if I know my change in y is 4, then I can just add that to the y value of 6 from my original point to get my new y value of 10. Now, another way you could think about this, just a more visual way that might help, is if when I go from 3 to 9, we agree that we're moving by 6 units to the right, and I have a slope of 2/3. So I know that means rise over run, so I'd be going up 2 over 3, and I can go up 2 over 3 twice within these 6 units. So I can go up 2 over 3, up 2 over 3, right? Up 2 over 3, up 2 over 3. So I can do that twice within my interval that is 6 units wide. And so as you can see, I went up 2 twice. So my change in y over that period of time is 4. And that means I'm ending up from when the y value is 6 at the beginning, I'm ending up at where y is 10. So that's another way to think about it. We can do the same thing for the next one. Change of x from 3 to 7 is 4, and then my slope is 2/3. So I can multiply 4 by 2/3 and get 8/3 as my change in y. And so again, I can add 8/3 to 6, because that was my previous point, to get my new y value. So I'm just going to write 6 plus 8/3 because I don't really feel like calculating it any further. So to kind of give a general idea of how this is going to connect to our Euler's method, what we just did is we took our change in x, and we multiplied it by our slope to get our change in y. And this makes sense because when we take the change in x and we multiply by the slope, we know we can write slope as change in y over change in x. And so as you can see, the change in x cancels out and we're left with change in y. So it makes sense that this process will work. And we're going to apply this same kind of like strategy or logic in our Euler's method, except of course change in y over change in x is going to be dy dx, okay? So let's do an example of Euler's method. F is a function that satisfies the initial value problem. So it's the solution to this differential equation, y plus x squared, where we have the point 0, 1 on our function. And we're going to use increments of 0.2 to approximate f of 0.8. So to start off, I'm always going to start with the point I've been given. So you really do need to be given a point to do Euler's method. So we know the point on our function 0, 1. So we're just going to start with 0, 1 as our initial point, and then we're going to use these increments of 0.2 to get to 0.8. And this makes sense because basically we're going to change by 0.2 until we get 0.8. So we're going to do the process 4 times to get from 0 to 0.8 because we're moving by 0.2 each time. Okay? So first things first, to use the same idea of like what we just did before, we're going to look at our point 0,1 and we're going to figure out what is the slope of the function at this point. Just like before, our slope was 2/3. It just was 2/3 at every point before. But for this, obviously, our slope is changing. So we do need to plug in 0, 1 to our differential equation, y plus x squared, to find out what is the slope at this point. So I forgot to write, this is the given initial value given to you. So I'm going to plug in 0, 1 to y plus x squared. So 1 plus 0 squared gives me 1. So that means the slope at this point of the function is 1. Now our dx is our change in x that we already are given, 0.2. We're going to be changing by 0.2 every single time. And then, so like our change in x every single time is going to be going by 0.2. And then to find our dy, this is where what we just did with the line really is helpful, is we know that we can get dy by taking dy dx and multiplying by dx. So we're literally going to take the value in our dy dx column and multiply it by the value in our dx column, 0.2. So 1 times 0.2 gives me 0.2 as my change in y. And now to get our new point, we're just going to move by that dx and move by that dy to our new point. So if we started at where x is 0 and our dx is 0.2, now we're at 0.2. And if we started where y was 1 and we're moving up by 0.2, now we're at 1.2. So to get your new x and y, you're always taking your old point x and adding dx, and then your old point y and adding dy. Okay, now we're just going to keep repeating this process. So like by the end, you'll be a pro. So let's repeat that process. Now I'm going to take the point we just ended with and start with it. So you always start where you just ended, 0.2, 1.2. Now to find my slope at this point, I have to plug in the point to my differential equation. So 1.2 plus 0.2 squared. Ooh, not cool. 0.2 squared gives me 1.24. And to get my dy, I have to multiply dy dx by dx. And that gives me, if you put it in a calculator, this is a calculator question. You couldn't do this without a calculator for this one. So you're welcome to plug it in and make sure you're getting the right thing. But when you put that in the calculator, you get 0.248. I'm not showing that. I'm just like doing it separately. And then now we just add on our dx to our old x and our dy to our old y to get our new point. So if I add on 0.2 to 0.2, now I'm at 0.4. Makes sense. I'm always going up by 0.2 from my last point. And then I'm going to add 0.248 to 1.24, which gives me 1.448. So again, I'm taking my 1.2. I shouldn't have said 1.24. I always look at that column and say the wrong thing. Sorry. To get your new y, you take the old y at the first column, add the dy, and you get the new y. So that's what's happening there. Okay, hopefully that makes sense. We're going to keep doing it so you'll see the pattern again. So again, take the point we just finished with and start with that, 0.4, 1.448. Okay, I got to plug that into my dy dx equation. So 1.448 plus 0.4 squared. Put that in a calculator, you get 1.608. Now I'm going to multiply my dy dx by my dy to get, my dy dx by my dx to get my dy. And when I put that in my calculator, 1.608 times 0.2, it gives me 0.3216. And then to get my new x and y, of course, we're going up by 0.2 again in the x, so we'll be at 0.6. And then I take my old y, 1.448, add the dy, 0.3216, to get my new y, which will be 1.769 when I add those together. one more time, we're going to take the point we just ended with and start with it. We're going to plug that point into our equation, 1.769 plus 0.6 squared, which gives me, I got to put that one in my calculator. I haven't done that one yet. 1.769 plus 0.6 squared gives me 2.129. Take my dy dx, multiply it with dx to get dy. So 2.129 times 0.2 gives me 0.4258. And then I'm going to add. So of course, now I'm finally at 0.8, which is what I wanted. That's my end goal, to approximate 0.8. And then I'm going to add my old y with my dy to get my new y. So 1.769 plus 0.4258 gives me 2.19. Did I write this all right? Times 0.2. Yeah, I'm getting 2.195. That's what I'm getting to the 3 decimal places. My notes say 2.196. So if I made a very small mistake, let me know. But maybe I just made a mistake before. So I'm getting 2.195. Yeah. That looks good to me. Okay. So that's my answer. That's it. So f of 0.8, our approximation using Euler's method, is 2.195. Okay. And we definitely needed a calculator to do that one. So that is the process of Euler's method. I'm not going to do any more on the video. I will post a key with the answers to the 2 multiple choice and the FRQ. You're really going to be doing the same method. Just some tips. They will always give you the differential equation, and they have to give you an initial point. They will also tell you the increments or the change in x to use, and they'll tell you what to approximate. So you're going to always be given that change in x. You don't have to come up with it yourself. And then you might be wondering, how do I know how many times to do the Euler's method? That's based on the change in x they give you and what you're trying to get to and where you're starting. So if I'm starting at 0 and I need to get to 0.8 and I'm going by 0.2, I'm going to have to do it 4 times. So that's all based on what is given to you. You'll be able to figure out how many times to do it until you get to what you're trying to approximate. So hopefully this helps. Let me know if you have any questions, and I will post a key with the answers to all the remaining questions. Good luck.